Question 2. The group 2 elements, magnesium to barium, are all silver white reactive metals. Part A, Roman 1, draw a label diagram to show the bonding and structure of group 2 metals at room temperature. So for metals, we see a lattice of positive metal ions, okay, that are in a sea of delocalized electrons. Electrons are delocalized, they are free to move, and we say it is a lattice because there is an attraction, there is a regular pattern, okay? So we have the metal ions here, they are in a pattern, they are in layers, okay, like that. They are positively charged, so just put a plus for all of them, and then in between them or around all of them we must have electrons, okay, which are negatively charged, delocalized. To be delocalized, that means you're not in one place, you are free to move. If somebody ever calls you local, then that means that you don't move, you don't even know what is happening around the world. You know, your mind, you are so stiff-necked, things of the sort, okay? So I will label and I say this one here is a metal ion, okay? We can say positive ions. And then this one here, I will say delocalized electron. So that is that. Roman 2, explain why magnesium has a higher electrical conductivity than sodium. Now for metals, remember to conduct electricity, it is the free movement of these electrons, okay? So the free movement of these electrons is the one that is responsible for the electrical conductivity. So the more electrons that are donated into this electron cloud, the stronger the electrical conductivity, okay? So magnesium has more delocalized electrons. That is what I have to say. Magnesium has more delocalized electrons, okay, than sodium, because magnesium forms this one here, meaning it loses 2 electrons, and sodium forms Ni+, which is in group 1, so it has lost 1 electron, yet this one has 2 electrons. As simple as that. Okay, then part B, write an equation for the reaction of magnesium with cold water. Now, the reaction of magnesium with cold water is a slow one, and here the products we get are the same for all of these metals in the group 2. We get a hydroxide and hydrogen gas, okay? And these metals are above hydrogen in the electrochemical series. That is why they are able to break down the water, okay? So we have magnesium, then plus hydrogen, water. We get magnesium hydroxide, then plus hydrogen. But then with steam, the reaction is very fast. And instead of forming magnesium hydroxide, it forms magnesium oxide. Okay, keep this in mind. It is also examinable. Okay, then we need to balance. Hydrogen here is 2 plus 2, that is a 4. That means I will put a 2 here to make the hydrogens 4. And then oxygens are 2 here. Oxygens are 2 here, magnesium 1, so it is balanced. Remember, the equation has to be balanced for it to be correct. Then part C, identify a single reagent that can be used to distinguish separate samples of dilute magnesium nitrate and dilute barium nitrate. So dilute samples of these ones, we are going to have magnesium ions, then we have the nitrate, okay? Then we also have barium ions, and we also have the nitrate ions. Now, we know that the solubility of sulfates of group 2 decreases down the group, okay? Let me write it here. Solubility of sulfates of group 2 elements decreases down the group. But then the solubility of the hydroxides increases down the group. Okay, so I will just get this, duplicate it, then I change where the sulfates are. I put hydroxides, not hydroxides. Group 2 elements, this one increases down the group. So solubility of hydroxides of group 2 elements increases down the group. Now, by the way, this word group is supposed to be, what happened here is an R missing. Pardon me here. So fix it there, group, then group. Now, that means if I put a sulfate, okay, a sulfate, this one will react with the barium and it gives you white PPT. But that sulfate with magnesium, it will remain there. The magnesium sulfate is dissolved. You see that? So that means I will bring a compound that has a sulfate. For example, any soluble sulfate that you want to see. But the reagent, the simplest one you can use here is sulfuric acid. Okay? Sulfuric acid, it has a sulfate there. Okay? And then when you react it here, what are you going to see? A white precipitate. Okay? Now, what are you going to have here? The explanation. We shall see that barium sulfate, or I can say, identify a single reagent that can be used to distinguish between the subordinate. So a single reagent is this one here. Explanation. Barium sulfate is insoluble. This is what I would say. Barium sulfate is insoluble. And magnesium sulfate is soluble. Okay? That is that. Then I can also bring maybe something that has gotten a hydroxide. Okay? For example, if I bring sodium hydroxide, now I will form magnesium hydroxide. I will also form barium hydroxide. Okay? I'll form these two. But since the solubility of hydroxides increases down the group, this one will remain in solution there. And then this one will form a white PPT. Okay? It's a solid. It will slowly form out. So I can also say, or if you don't write this one, now in the exam, don't say this or no. I'm giving two answers for you, pick one. Or sodium hydroxide, it's a soluble hydroxide. Then that means we can have, so where I'm putting the dots, if you use this one here, then its answer will be here. We shall say that magnesium hydroxide is insoluble and barium hydroxide is soluble. This would be the answer for this one here. So that is that. Part D, Roman 1. Describe what is observed when strontium iodide reacts with concentrated sulfuric acid. Now, for these salts of hydrates, I mean the salts of these halides, usually in the books you have, let's say, sodium. In the books there is sodium iodide. So this one reacts with sulfuric acid. The first reaction is the one for it is called an acid-base reaction. So we get sodium hydrogen sulfate. You see that? Then plus sodium hydrogen sulfate, then you have hydrogen iodide. Now, because this one is not as strong as sulfur, as sulfuric acid, so this one is going to be broken down. This one is more of a reducing agent, this one is an oxidizing agent, so it can be broken further. And when it is broken, you are going to receive, there are three equations you can get from here. You can get iodine, you can get sulfur dioxide, and then water. But of these three equations, iodine and water are the products that are common to all. Okay, they are there. But then you can have here sulfur or hydrogen sulfide. I'm not going to balance these equations, okay, to save time. But then for bromine, you only get something like this. If you have hydrogen bromide here, then it will be broken down by sulfuric acid, and then you get bromine, sulfur dioxide, and then water. That is for bromine, okay? Then for chlorine, if you have sodium chloride here, it only ends here. The hydrogen chloride cannot be broken down further by sulfuric acid because hydrogen chloride is a stronger oxidizing agent compared to sulfuric acid in that case. So it is the same thing here because this one is in solution there. The ions, the iodide ions are there. So they are broken down. So it is going to be the same process here. So now these are our products. So we are going to give the observations based on these ones here. Sulfur is a yellow solid. So I can say a yellow solid. Okay, basing on sulfur. Then iodine is a gray solid deposited. So I can say gray solid. You see? What else? Hydrogen sulfide. What do you know about hydrogen sulfide? It has that smell of rotten eggs, right? So I can say rotten egg smell. Rotten egg smell. You see that one? Then iodine can appear as gaseous. If it is a solid, it is gray or black. Okay? Then it can also be purple. It's a purple gas. It can come off. Okay? Like that. Okay? You just give according to, even this one, sulfur, this gas here. So I just say, if you don't know the color of that gas there, then you just say effervescence. Because the gas is coming off. Just say effervescence. Effervescence. Because you really need to know the spelling here. Okay. Roman 2, compound X, an anhydrous group 2 bromide is dissolved in water and titrated against aqueous silver nitrate. A solution containing 0.250 grams of X requires 33.65 cubic centimeters of 0.05 moles per liter of silver nitrate for the complete reaction. Identify X and show your working. Okay. Now, the first thing we need to know is to write the moles. To get the moles, we begin with the standard solution. The standard solution is the one whose concentration is known. Okay. So we have its volume and then we have its what? Molarity. So what we are going to do here is to find the moles. Moles of silver nitrate. Moles of silver nitrate, we are just going to get this one here. Then we divide it by 1,000, then times 0.05. Or using first principles, this is what I can write. This statement here, this is what it means. That 1,000 cubic centimeters, because that is the liter, okay, of solution contains contains 0.05 moles, okay, of this one here. How about the 33.65 cubic centimeters of solution? This one will contain 33.65, then times 0.05, then out of 1000. So that's why you find that they get this volume, they divide it by 1000, and then they multiply by that, okay? So that is that. So you just get the volume, then you divide it by 1000, and then times the moles here given. So what do we get here? 33.65 times 0.05, then divide by 1000. This one gives us 1.6825 times 10 to power negative 3 moles. Now we need a stoichiometric equation. So let's say that metal, I don't know it, okay? Let me represent it with an M. It can be barium, it can be what from group 2, okay? Barium, magnesium, whatever. So let me write it as M. Then we have bromine, of course. This one has to be like this because that group 2, it has M2 plus, and then bromine is having a minus. So that means I need 2 of these to balance this, okay? To balance the 2 plus here. So that is what we are going to have there. So plus, then silver nitrate. Then what do we get from here? We shall get M nitrate, then plus silver bromide. And this one comes off as the cream precipitate, okay? Cream precipitate. Then let's balance. Of course, nitrate, here it is 2, so I'll put a 2 here. When I put a 2 here, then silver, I will have to put a 2 here. And of course, bromine is 2 here, so it is also here too. So that is the balanced equation there. Now, from here, 1 mole of X here reacts with 2 moles of this. So how do we move from the 2 to the 1? We divide by 2, right? So that means we shall write moles of X or MBr2. This one will be equal to a half of what we have gotten here. So 1.6825 times 10 to power negative 3 moles. Okay? Then from there, these moles here of X are the ones that weigh this one here. Okay? They are the ones that weigh this mass here. So I'll say, by the way, what is this one times a half? I'll come to this one, then I say times 0.5. That is 8.41 times, 8.4125 times 10 to power negative 4. 8.4125 times 10 to power negative 4 moles. Okay, so I will say these moles 0. No. It is 8.4125 times 10 to power negative 4 moles of, let me just use X, okay, they weigh this 0.250 grams. What you are looking for, you put it on the right. Now, from here, we know that for a compound, 1 mole of a compound weighs its molecular mass. So how about 1 mole? If these moles weigh this, how about 1 mole of X? Okay, so 1 mole of X will weigh, then you get this 1 times this, then divide by this. 1 times 0.250 out of 8.4125 times 10 to power negative 4 grams. Okay? Or you also know that mass, number of moles is equal to mass over the MR. So if I need MR cross multiply here, you will get MR, which is equal to mass over number of moles. So you see this mass here, then divide by the number of moles. So that is that. And I like using from first principles. When I write statements like this, that is calculating from first principles. So what do we get here? I'll get 0.250, then I divide by this answer. 0.250 divided by the answer. That is 297, and the rest of those figures, 297.1768202. Okay. Now, this one actually will approximate to 297.2 if I write it to 4 significant what? Figures. Now, we are having MBR2. So the MR of MBR2 is equal to 297.2. Okay. So I have M here, then plus 2 times bromine is 79.9. Okay. Then I equate to 297.2. So what will be the value of M? I'll get 297.2. Then I subtract 2 times the 79.9. So what do we get here as the value of M? 297.2 minus 2 into 79.9. That is 137.4. 137.4. Remember, this is now the AR value of a group 2 element. Then I go to the periodic table. Okay. Then I check for that one there. Go to group 2. So when I go to group 2, it is here. Calcium is 40. Calcium is 40.1, strontium 87.6, barium 137.3. And yet the one we have is 137.4. That means M is barium. Okay, so I'll go back and I write barium here. So this one corresponds to barium. Now X is barium bromide. As simple as that.